So I'm going to talk about assumptions in cryptography and how it might make some slipping problems for cryptographers and how we get to handle that, basically. Okay, so let me start by showing you a list of 7 math problems. I'll tell you in a moment how it relates to crypto, but these are pure math problems, 7 of them, listed by Clay Institute of Mathematics in 2000. And they're called millennium problems because if you solve any of them, you get $1 million. Unfortunately, one of them is solved, so we have only 6 to try. But the one that has to do with this talk is a problem. It has a fancy name, but we don't need to know what that letter P and NP means. But the question is called P versus NP problem. It's a question about mathematics itself. It's kind of a reflective question. But it's interestingly enough, it's very easy to describe what the problem is going to be about. So the letter P here refers to a set of problems which you can think of them as puzzles that are easy to solve. Think of any puzzle that you can easily solve with like a human brain or with your laptop, your cell phone. On the other hand, NP refers to a set of puzzles that are not necessarily easy to solve, but once you're given the solution, you can easily verify that you have the solution. Think of Sudoku. Like, it might be very hard to solve Sudoku on a huge like 1,000 by 1,000 matrix. But once someone gives you the solution, you can write a simple program that verifies the solution in seconds, even if it's a huge instance. Or crossword puzzles. Any puzzle that is hard to solve, but once you're given the solution, you can easily verify that you do have the right solution or a right solution. This question is asking whether there is any hard puzzle. It's asking as simple as that. Is it the fact that Sudoku on large instances, it's hard because we don't know how to solve it, or there is a mathematical reason that there is no algorithm to solve it? So this question is asking whether there is any hard puzzle. So if P is equal to NP, it means there is no hard puzzle. We can solve all of them efficiently. And these things should be formalized efficiently, like fast algorithms. What do they mean precisely? Well, we can formalize all of them 100%, but let's keep it intuitive at that level. So let's see one example, that one particular puzzle that relates it to cryptography and how this question is related to cryptography. Think of the following puzzle. We are given a number n, and this n is just a product of 2 other numbers, p and q. We are not given p and q. We are supposed to find it. We are supposed to find the factoring of n. So the solution would be the pair p and q, and the puzzle would be n. You might say, well, this is an easy problem. We can solve it. We know how to solve this puzzle from elementary school. All we have to do is to try to divide n by 2, 3, 4, and as soon as we have found p, we divide n by p, we get q. So what's up with this puzzle that might be kind of hard for some mathematicians to solve? The problem is that this simple solution would take billions of years, even if you just run it on a number which has, say, 1 million digits. A number with 1 million digits is something that we work with in computer programs every day. It's something that we can represent very efficiently, but factoring that number is hard. Why? Because the number with 1 million digits is not 1 million, it's 10 to the power million. And if you run that algorithm, simple algorithm, it would take years, not just years, decades or more than the age of the universe just to factor a number of million digits. That's why this puzzle is considered a hard puzzle. We don't have an algorithm to solve it. However, if someone gives you the factoring, you can easily verify it. You just have to multiply those 2 numbers. Multiplication is very fast. Even huge numbers, we can multiply them in seconds with our cell phone. We don't need a supercomputer for that. So there is a huge gap. We can verify solutions for this puzzle. We don't know how to solve it. So it's a problem in NP. We don't know whether it's in P. So we don't know whether it's easy. We don't have a proof. However, nobody knows how to solve this efficiently. So it's a big open question, and we don't know the answer. How is this puzzle related to cryptography? Interestingly, this puzzle is at the heart of the most popular encryption algorithm that you would use it every day, probably without knowing that you're using it. Whenever you log in on your email account, whenever you buy something on Amazon, this encryption algorithm is used somewhere in this process over the internet. And the name is RSA. It stands for Rivest, Shamir, and Edelman, three guys who invented this encryption algorithm. The point is that the secret key in this encryption algorithm that guarantees the security is the factoring of a number n. And this number n is publicly known. Everybody could know this n, but nobody knows this factoring. So it's like someone who wants to break this encryption algorithm, they really want to find out this factoring, and that's not public, that's secret. We don't know how to find that secret value. That's why this is considered to be secure. Do we have a proof for that? Do we have a mathematical proof for that? That's not just we don't know, nobody can compute this P and Q in a reasonable amount of time. That's something we don't know. Then that's how this P versus NP question is tightly related to the heart of the most popular encryption algorithm. If that conjecture, which as I told you, it's open, is resolved positively, if someone proves someday that P is equal to NP, what they show is that you can actually factor large integers efficiently, which means that you can break RSA. Well, that's not something really good. So there is an open question that if it's solved differently than what we hope, would make basically all these secure protocols insecure. All of them could be broken. And I want to emphasize, this is not really an issue about RSA. The same argument, you can apply it to every single encryption algorithm that we're using. Not just RSA, not just the modern cryptography, everything that has been invented throughout the history suffers from this issue, that if this conjecture is resolved this way, they would all be insecure. And so one of the benefits of modern cryptography is that at least we are aware of these issues. We understand this mathematical problem that is at the heart of the security of our systems. We were kind of unaware of it maybe 60 years ago. So we have an issue here, and as I told you, the issue is much worse. We don't have any secure encryption if P is equal to NP. And in a way, I rephrase the situation. The assumption that P is different from NP is an assumption that we are implicitly making when we are using RSA. We are assuming that this problem is hard. There are, in fact, hard puzzles that we don't know how to solve mathematically, provably. The situation is even worse. This is not this only assumption that we use in cryptography. There are tens of other assumptions. And by assumption, I mean things that we don't have a proof for, but we believe this is the case. We assume this is the case. We prove it to be secure, assuming that assumption from mathematics. So I hope you realize that there is this big problem here that we have in case this P happens to be equal to NP. And with that description, I want to kind of tell you what the picture of modern cryptography looks like through an eyes of a cryptographer. We feel we are in a heaven. Basically, every problem that you give us in a matter of months or weeks, someone can propose you a way to solve it in a secure way. And it's not just about encryption. Think of other things like how you prove your identity, how you sign a message in an electronic way. Tons of other questions that have security notions attached to them. As soon as we formalize them in a good way, we can solve them, and we have solutions that nobody can break. However, all those security is held by this pillar. So we have this assumption that there are some computational problems that are hard, and that is the basis for the security. If someone kind of breaks that pillar, there's nothing going to be left in that wonderful world. They all would break down. So this is the real picture. There is a pillar over there. Which leads me to the question of this talk. Well, if there is this pillar that might break someday, how do cryptographers feel good? So, we design things and people use in practice, and we don't have a really proof that this is secure. Someday it might break down. And that might give us this slipping problem. Well, one solution proposed by Sylvia Micali, a recent Turing Award winner, is that, well, they do not. In fact, cryptographers do not disable. That's how he kind of manages the situation, I rephrase the question, well, can we sleep better, at least? And I'm going to tell you 3 ideas that cryptographers and modern cryptography has tried to remedy the situation. What can we do about the fact that we have assumptions, not theorems, that we use in cryptography? The first idea was proposed by Deviant Hellman. These are the guys who invented the so-called public key cryptography. How can we talk over the internet without even sharing a key ahead of the time? And we start to talk to each other, a third person wouldn't understand what we are talking about. That's kind of a magical thing when you think about it. They said, well, they were aware of this issue, that there is an assumption behind the security of the systems. They said, well, this assumption is behind everything we know. Can we make it the only assumption that we are making and try to get rid of everything else at least? Make this assumption and nothing else. Unfortunately, so far we haven't been able to make this proposal work. And toward the end of my PhD research, through a line of work which started from '79, we basically get to the understanding that this proposal might never work. So we might need to really make this assumption and 10 other assumptions or 100 more assumptions to prove the security. So we cannot get away from these assumptions. We need many of them to prove the security of the systems. The second idea, which actually it's beyond an idea, it's maybe a theme in modern cryptography for the last 40, 50 years, says, well, if we cannot get rid of these assumptions, as long as we cannot prove these problems to be hard, how about we learn how to manage them and live with them, have a theory that lets us understand them better and use them the right way? What do I mean? If we want to have a good theory about assumptions, that theory, for example, should let us understand when 2 different assumptions that look completely different are in fact the same assumption. For example, the problem of crossword puzzles or Sudoku, they look completely different, but through this theory, we understand that both these problems are actually the same. If you solve one of them in a mathematically formalized way, you can actually solve the other one. They're both NP-complete in a sense. And we have a theory that also lets us know which assumption is weaker than the other one, which one of them are safer to use, which one of them are more likely to be false, which one of them are more likely to be true, so that we use the better and better assumptions. Whenever we can use a better mathematical assumption, we switch to that. We kind of have a safer system in a kind of heuristic way. And finally, this theory should let us formulate these puzzles in a way that it motivates mathematicians to work on them. Because if you give a mathematician a nice problem, a cute problem, they would work on it for tens of years. And if they can't solve it, if they can't solve, for example, the factoring puzzle after 100 years of work, well, that's a good point that we can use this problem. Even though it's not solved, we can use it to build a secure crypto system on top of it. At least we have 100 years of research that kind of justifies that crypto system. Finally, I want to tell you the third idea that I personally find it quite amazing, which aims at essentially getting rid of these assumptions, computational assumptions, which you might be a little skeptical, but Zakai kept telling you that we don't know how to get rid of assumptions cryptography. The point is that we try to get rid of computational assumptions like hardness of factoring or these puzzles that we use. We use different type of assumptions from physics, physical assumptions. What do I mean by that, using physical assumptions? The first time that this idea was proposed was, I think you can kind of give the credit to these 2 geniuses from '84. They proved the following interesting statement. They proved that if you're willing to make the assumption that quantum mechanics is the real law behind the universe, you can actually design algorithms for cryptography that is provably secure. So in a sense, we are still making an assumption. We are assuming that quantum mechanics actually governs the universe. But we are not making assumptions about hardness of factoring. We are not making assumptions about which puzzles are hard to solve. We are using a completely different type of assumption. And don't forget, we cannot really prove the laws of the universe to be something, because all we can do is start from some assumption about some basic laws and derive from it other theorems. And quantum mechanics is the current champion, so we don't have any better theories at the moment. What they showed is that you can use this type of assumptions, physical assumptions, and get rid of computational assumptions. So this might look completely different, but don't forget also the other direction. When we are making assumption that some problems are hard to solve, when we say it's hard to solve this puzzle or hard to solve that puzzle, we are also implicitly talking about something about real world. We are saying that there is no computer that you can build, even a supercomputer, that can factor numbers. Even though you didn't talk about physics, we are implicitly talking about some limitations of the physical world. There is no physical way to do this or to do that. So in a sense, these guys are just being more straight to talk about the laws of the physics being used into cryptography rather than going indirectly. And this is the direction that I found quite astonishing to follow and try to get rid of computational assumptions as much as possible. So I want to tell you one specific idea that is inspired by this work. And the idea is to try to use assumptions about hardware rather than assumptions about software. So when I tell you it's hard to factor integers, what does it mean? It means that we have no algorithm, we have no mathematical method that lets us factor huge numbers. That's something about algorithm, that's something about software, about the logic of computation. How about making assumptions about the physical properties of hardware? In particular, the assumption that is explored in this context is the assumption that we can build certain hardware that looks like a black box. So this hardware would hide an algorithm in it. So as you can see, there's a circuit there. That circuit is essentially an algorithm. You can give it an input, it gives you an output. If we can build a piece of hardware that lets you run that algorithm, but at the same time, it's secure in a sense that you cannot really find out how this hardware is running this algorithm. It looks like a black box to whoever holds that piece of hardware. Whether we can build such an hardware or not, it's a question about, you can approach it from, again, physics. Maybe we can prove that some piece of hardware has this property because of the laws of the physics. Or we can build it and believe it to be the case just based on some technological reasons, that nobody with this level of technology can break into this piece of hardware. And that's why it's called a tamper-proof hardware. If we can build such a piece of hardware, which we have evidence that could be done, we have some little pieces of hardware that whoever makes them claims to be tamper-proof, and things are getting better and better in that direction. If we could eventually build a tamper-proof piece of hardware, the situation would become very interesting. We know the theory of how to use tamper-proof hardware. So this happens over and over, that the theory is kind of ahead of the practical side. Just like quantum mechanic-based algorithms, that we have designed the algorithms, but implementation is falling behind. We also have a theory here that says if we can build tamper-proof hardware, we can get rid of computational assumptions for a variety of scenarios. For example, we can have protocols that essentially let you have a secure multi-party computation. You have several parties, they have inputs, they want to jointly compute an output. For example, they want to run a voting. Each have a vote, we want to take the vote, but we don't want to reveal the votes to each other. Or we want to do a secure auction, or many different applications that fall into this framework. We know how to do this securely by using tamper-proof hardware without relying any computational assumptions. So we wouldn't be worried about whether someone can factor integers or someone can prove p equal to np. But we have a different type of assumption which is of a completely different nature. It's a physical assumption about a physical object. And we hope to be able to get security from it. For a large case of scenarios, we know actually how to do it. So if I want to summarize what was the third idea giving us in cryptography, going back to this picture that I showed you, we again feel that we are living in this wonderful world, that we can do lots of things in a secure way. But we have two pillars now. One of it was computational assumption. We have one more that could help us hold this wonderful world up there. And that's what I call the physical assumption. So now, if one of these two breaks down, at least we have something else that we can build a secure system on top of it. So they together would hold the situation for us, and that might be one way to say that we feel safer and we can sleep better at night, because even if one of them breaks down, we at least have something that can give us security and secure systems based on a different type of assumption. With that picture, which looks a little safer than the previous one, I want to end the talk, and thank you all.